Right, so I want to show you the thoughts behind us doing the topic which we're doing right now. Students, I want you to see how fast we can do the whole chem syllabus, okay? I want you to see how fast we can cover everything in chem and actually be done. So we want to do a certain section. Yes, I'm gonna open a paper and show you. Let me just first before I open the top. Look at this, everybody. This is all we have to know to be done with chem, okay? We've covered a lot of the things here, actually. We've covered a lot of the things here, but we're still going to go through them again because this is the time. This is the time when we're doing it. We brush up together, we brush up, we do it until we are all convinced that we are good. We're good at something. Look at how small chem is. Huh? For acids, bases, and salts, we kind of did I do it with you or was it with the other class? Was it with you guys? It was with you guys, right? I'll still give you the notes so that you can have them of the things we did. And for metals and chemistry of the environment, which we just finished. And we did organic chemistry, which we did again. And these two, and this one, and this one. So here, these are the topics I want to make sure we are mastering and we can do questions on. Huh? Even periodic table and even chapter 12. We'll try to do as many as we can in the next few days and see how to try and prepare people for mocks. I'll be doing some other small clips when I can as well to send to you guys. Send me the topics you need first so that I start with those. But listen, everybody, let me tell you something. The topic of organic chemistry, when they give you a question, usually the first part has chapter 5 and chapter 6. And that is the reason I'm going to make sure you know them, okay? I've talked about chapter 5 already, but I'm just going to revise with you today. And next lesson we do chapter 6, or we can do it even today, I don't know. But we want to do chapter 5 and chapter 6, so that when we do a chapter 11 question, and I revise it with you again, you're good. So we want to do chapter 5 and chapter 6, and link it with chapter 11. I'll give you the best organic chem notes you've ever had. The best. I'll give you. I'm fixing, okay? I'm fixing. Chapter 5, chapter 6. We'll go through them very quick as preparation to chapter 11. This is short. It mustn't take us long. Right. Let me open a past paper just to show you what I'm talking about so that you guys see how important it is. Because I want you to know chapter 5 and 99% of the times that you are going to do a question on chapter 5 or chapter 6, which is endothermic and exothermic reactions, those things, and also questions on rate of reaction and equilibria, these things, these words. 99% of the times you will meet them, they will be stuck onto an organic chemistry question. And I want you to wake up. I want you to see the part which is from chapter 5 and chapter 6. Then I will need you to see the part which is from chapter 11. So this is the most important thing. If I can make you see that, then I will be a happy man. Let me open so that you see what I'm talking about. This is the paper you guys are writing this year. You guys are writing for option 1. Have you seen your exam timetable? Do you look at your exam timetable? You don't? Okay, good. Here they asked you about chapter 5, a bit about chapter 5, in what looked like a separate question from organic chemistry, so this was a little bit different. But look here. Look at this. Okay, this was nice. They made it obvious for you guys. And just look at it, okay? For this, at least for this question, look here, guys. This is chapter 5 and chapter 6 being asked. Anytime they ask you anything to do with energy or enthalpy, it's chapter 5, okay? Chapter 5 is the one that talks about energy and these type of diagrams. Therefore, energy. Anytime you see the word energy, you are in chapter 5, okay? So this is chapter 5. It's an energy profile diagrams. Here, bond energy. Again, chapter 5. Then you keep going down on the same question, okay? Bond energy, bond energy. Then look at them now. They are using the word equilibrium. The word equilibrium is from chapter 6 now. Similar question, everything the same. It's just part C of the same question. Now they're asking about bond energy. They want you to now know equilibrium. No, they're asking about equilibrium and collision theory. This is now chapter 6. So these things come as one thing. When you do them in class, they look like different chapters. But wake up! Chapters 5, chapter 6, chapter 11. Don't let me down. Okay? Chapter 5, chapter 6. Don't let me down, students. They are going to come together. Are we together, guys? Students, are we together? Guys, chapter 5, chapter 6. I want you to know things that don't ever be shocked. Don't ever be shocked in the exam. We already know that's what they're going to do. So we should, when we know chapter 5, we should know it one time with chapter 6. Know everything together one time. And do these questions. They'll be packed together. And sometimes they give them in front of organic chem to try and fool us. You see an alcohol, but they are not asking anything to do about it, anything to do with its reactions or general. They'll be asking rate, bond energy. If you see these words, it's not anything to do with organic chem. It could be an organic chem substance, okay? But that doesn't mean that it is an organic chem question. Wake up! They put chapter 5 and chapter 6 as part of organic chem. Don't think of organic chem when you are doing those questions. I'll show you more. Let me see if they did it here. Let me see if they did. I just want one where they did it to prove and make sure everybody agrees with me for good. To say, sir, you know what? You're right, sir. These guys are going to try and catch us this way. We are not going to fall for that trap, sir. This is acids and bases, eh? Let me show you. This is actually organic chem because they're asking about empirical formula and whatever. So that's not a problem. Look at this one. I'm going to open 4 or 5 papers. You're going to see it. Okay, almost. This was almost what I was talking about, but this is not organic chem compound. But this reaction could be organic chem. And you see them say the word rate. This word rate, this is, when you see this, once you see the word equilibrium, rate, this is from chapter 6, which we'll just go through in 5 seconds tomorrow or today. Okay, here, look at this. This is what I'm talking about. Right. Can I ask you a question? Where did you learn about ethene? Guys, where did we learn about ethene? Where did we learn about this guy? Which topic is it? Topic number what? Students, tell me first. Topic number what? Topic number 11, right? Organic chemistry, right? Does everybody agree with me that this word ethene, yes, this is organic chem. Look at how they are trying to catch us. They give you organic chem. Then when you start thinking about organic chem, reactions, dichloroethane, reactions, then dichloroethane, reactions, you're thinking about reactions. Then you see the word bond energy. Don't let them fool you. This is not organic chem. There is nothing to do with organic chem on the word energy. This is chapter 5. So they can give you things you do in organic chem, but the moment if they ever ask you anything to do with chapter 5 and chapter 6, don't think about organic chem. Think about chapter 5 and chapter 6. This is energy, so this is chapter 5. Think about what we do in chapter 5. I know this is organic chem compounds, but this is not an organic chem question. This is not empirical formula. They're not asking for reactions. They're not asking for isomers. They're not asking for polymers. So why would I think organic chem? Why? Why would I think organic? Don't let me down. Wake up, guys. A lot of people think chem is hard, organic chem is long, because they'll be reading this as organic chem. It's not organic chem. This is chapter 5. This is not organic chem. Yes, it's an organic chem compound. So what? But they're not asking anything to do with it. Organic chem starts when they start asking organic chem questions, which they will. Of course, we know they will. At the end here. Let's see. Yeah. Molecular formula, empirical formula, products and catalysts and reactions. This is now organic chem, eh? This is now organic chem, but not what we were dealing with. So anyway, chapter 5, chapter 6, I'm going to find you. I want you to promise it, eh? Promise it right now. To say chapter 5, chapter 6, man, I'm going to find you in the test. Even if you hide in organic chem, I'm going to find you. So let's see now what you guys should know. Let's see. You should find it. Right. Anyway, there are some few things that I was putting here. This is a very small topic, and I don't want you to focus on the wrong things. Just a few definitions and the one calculation which is going to come, the bond energy calculation. But you should know the diagram, the energy profile, enthalpy profile, or you can say the energy profile diagram or energy change diagram. And you should know a few things. So anyway, I want you to know this. Everybody, we are dealing with chapter 5, and chapter 5 is exothermic and endothermic reactions. This is chapter 5. It's called chemical energetics. Chemical energetics. Let's quickly just look at the 4 things you must know. We wrap it up and we know we are done. Chemical energetics. Number 1, you must know the first thing here. What is this chapter about? What is this chapter about? Everybody should know that anytime you see a reaction, there's energy being transferred, okay? When you see things reacting, energy is being transferred either this way or that way or outside. But energy is transferred anytime you have a reaction. Anytime you have a reaction, energy is transferred. Now, here we are saying, how is energy transferred? Okay, this I'll say it later, this statement here. I don't want to say it right now. Energy transferred. Now, when you're dealing with a reaction, you want to know, is energy transferred into the reaction, or like into the vessel which we are reacting, or is energy going out? So we have a place where a reaction happens. Reactions don't happen in the atmosphere. They happen in a container, whatever container you are using, beaker or whatever. You have this beaker, you have your reactants inside and stuff. So we want to know, as reaction is going on, is energy going out or energy going into the thing? And I'll tell you how you know. First, you must just know that it's important. Yes, LGK I didn't hear you. Yes. I'll give you just now. I'm almost done. Let me put them in there. Let me send them to you. All right, I sent. So they'll get there just now. I sent them. Right. Anyway, I was saying, when you're knowing this, you should know. Number one, everybody, you need to know when a reaction happens, energy is involved. Okay, energy is going to be involved. So we want to know, as the reaction is going on, is energy coming out or is energy going in? This is very important for you as a chemist when you are planning a reaction. You are planning a reaction, you need to be able to know this reaction, does it release energy outside or does it? So when you're dealing with it, the place where your things are reacting, this inside here, we call it the system. So system is here. Then everywhere here, we now call them the surroundings. These are now the surroundings. So you have the system, then you have the surroundings. Surroundings mean everything else that is not the reactants. Anything else from the vessel to the atmosphere around it as well, all this is surroundings. The system is what is inside. So we want to know, is heat being lost to the surroundings or is heat being gained from the surroundings? Right. So the system is the chemicals that are reacting. Then everything else outside the chemicals is the surroundings. Anything else from the container to the air or whatever that will be around the chemicals, it will be the surroundings. Now, everybody should know this is the most important. Then, when we have a system that loves heat so much, that loves energy, when we have reactants that will not react until you heat them, reactants that will not react until you heat them, those reactants, we say they are endothermic. They love to have heat entering. Enter. Endothermic. Endo means to enter. Endo means to enter. So therm is heat. Endothermic is a reaction that absorbs energy from the surroundings. The surroundings will get cooler because all the heat is going. So when you hold this type of a reaction, it feels colder. The reason it feels cold is because it's taking the heat. So it's leaving the outside being cold. Then an exothermic reaction is a self-powered reaction. It's like burning firewood. When you burn firewood, it does not need you to put energy. It gives you energy. You can actually sit and warm yourself as the reaction is going on. This reaction is releasing energy to the surroundings. So energy is coming out of the system. When you hold the container, it must feel warm. For an this is an exothermic reaction. There is no heat source. It is releasing heat on its own. That's an exothermic. So now, when you are finding out, okay, we've told you what these are. We've told you what goes on, but that doesn't mean as a chemist you now know, because that's not what you get. You will get a reaction like the one I just showed you for organic chem. Then you have the job of finding out that reaction. Is it exo or endo? You now need to find out. And for you to find out, Mr. Chemist, there are things you must already know. You must already know some things. The things that you must already know, number one, is that when we have a reaction now, a real reaction, there are two processes that happen in one reaction. It's one reaction, but there are two things that happen. You are having hydrogen plus oxygen reacting to give you water. Okay? Something like this. Giving you water. Now, what you must know is that for hydrogen to ever react with oxygen to give you water, we must break the bonds that are holding this together. So we break the bonds that are holding the hydrogen together and the oxygen together. Then when they are separate, we join them and form something. So there's going to be breaking. We're going to break this, break this, then you will form this. So does this happen for every reaction? Yes. So for every reaction we have to break before we form? Yes. That's why you need what we call activation energy. For every reaction, you need to break before you form. Now, the game is going to be when we want to find out, because what we will feel or see is the overall effect. But now you are chemists, you are smart now. You know that, okay, I'm going to see the overall effect to say, is this exothermic or is this endothermic? That's what I will see. But in reality, two things are happening. There is breaking first, and then there is forming second. Whether the reaction is endothermic or exothermic, we don't care. Two things happen in every reaction. Reactants are broken down, then you then form the product. If you don't break down the reactants, you are forming nothing. So from now on, I want everybody to know, every reaction has two stages: bond breaking and bond making. Bond breaking, whether it is endothermic or whether it is exothermic, to break anything, you need to put some energy. You want to break a stick? Put some energy. You want to break anything? Put some energy. If you want to break a bond, you need to supply energy. So bond breaking takes in energy. It absorbs energy from surroundings. So for a reaction to occur, the reactants are going to need to break the bond energy they have. Okay, they need to break the bonds, and this absorbs energy from the surroundings, breaking the bonds of the reactants. In every single reaction this happens. Every single reaction. Then after that, okay, you now need to make bonds of the product. You now need to make bonds of the product. How? By releasing energy. I don't care whether you agree with it or not. Automatically, you should know that bond breaking was needing energy. It was endothermic. It was absorbing energy from the surroundings. So automatically, you must know that when you are now forming bonds, it's the opposite. I say, how can forming bonds release energy? What does that make sense? Hey, just know it for now, from today onwards, forever and ever, that forming bonds, it releases energy to the surroundings. So say, are you meaning to tell me that in every reaction, two things are going to happen? Energy is going to be absorbed from the surroundings, and energy will also be released to the surroundings? Yes. So in every reaction, there's going to be these two. Yes. Energy is absorbed, then released also. Yes. So how do you then say this is an endothermic reaction which releases energy when it does both? Why do you do that? Because when we say it takes in energy, endothermic takes in energy, okay, from the surroundings. When we say it's an endothermic reaction that takes in energy from the surroundings, we are saying it took more energy than it released. So when you were breaking the bonds, you used 1,000 joules. Then when you were forming the bonds, you only released 400. So don't cheat us. In other words, overall speaking, this reaction, it took more energy than it gave. So we can say that this reaction takes energy from the surroundings. So it's endothermic. Endothermic reaction is a reaction that absorbs energy from the surroundings. Does it mean to say it doesn't also release? It releases. Of course, those two things will happen. But when we say it absorbs energy from the surroundings and it's endothermic, we are just trying to say it will absorb more than it will release. And it will, when you calculate the energy, you get a positive answer to mean it's endothermic. Okay, it absorbs more energy than it releases. It takes in more energy than it will let out. That's an endothermic. An exothermic reaction is obviously one which releases. So this one absorbs energy from the surroundings. Exo to exit. Exothermic, it releases energy to the surroundings. Why? Does it mean it also doesn't absorb? It will absorb at bond breaking. But the amount it will release is much more than the one it absorbed. Please. All right. So here, no, this one you do it on your own. Here, breaking, it takes in energy. Why does it take in energy? To break the bonds. Okay. They move into, why does bond making release? Why does bond breaking absorb energy? To break the bonds. Bond breaking always absorbs energy. So when we are breaking bonds, we absorb energy. When we are releasing, when we are releasing energy, we are forming bonds. When we are forming bonds, we are releasing energy. Energy is going out. Energy is going out. Okay, it's not going in, it is going out. This is bond formation. Energy is going out. Right. So now, here they just need you to know the diagram, which I'm going to show you, the energy profile diagram. And this here they are showing you what an exothermic reaction is. A reaction that transfers energy from the system to the surroundings. It releases energy from the system to the surroundings. Okay, I don't want to see this. Characteristics of exothermic. Delta H is going to be a negative value. When you do your calculation, because we will need you to calculate. When we say you are calculating delta H, you are calculating the overall energy transfer. To say overall speaking, was more heat released than taken in, or was more taken in than released? If you get delta H, which is enthalpy change, which is the enthalpy change, or the heat transferred, this in simple terms we can say it is the heat transferred during a reaction. If you get the heat transferred being negative, it means it was taken out. That's an exothermic reaction. It is busy losing energy to the surroundings. It's busy losing energy. So at the end of the day, the products will have less energy than the reactants because it lost energy to the surroundings. It was busy losing energy to the surroundings. When you go to a container where an exothermic reaction is going on, it will feel hot. So what are key things that a person must know if they know exothermic reaction? They must know that an enthalpy or thermal energy is taken from the system to the surroundings. Okay, and the temperature of the surroundings increase. The temperature of the surroundings. Temperature of the surroundings. Because the reaction is producing its own temperature. So the temperature of the surroundings as well will be going up. The energy of the products is less. Products are in the system, my friend. Don't say because temperature is going to the surrounding, you say then the products have more energy. You're saying what doesn't make sense. Make sure you know this. Products have less energy than reactants. So they need you to now know the energy profile diagram of this type of thing. Let me show you right now so everybody knows. When you're doing an exothermic reaction, they will need you to do the energy profile diagram. You show it like this. Reactants, at the end of the day, should have more energy than products. So here you put your products, whatever your products are, you go and take from the reaction. Then here you put your reactants. Everybody can see that we have lost energy here. Reactants were high up here. Now look where products are. Remember to always first start by going up, then go down. First go up all the time. Now this going up from reactants to the top of the mountain, we call this the activation energy, EA. Then from reactants to products, here's how you do it. It's always from reactants to products. You can't start at products. How can you do that? This is your delta H. I don't care whether it's going up or down. It starts from reactants going to products. Now, because it's going down, this delta H, it is going to be negative. That's what we know. So this is what we did not say products will have negative energy. Don't say what nobody said. Why do you love to do that? Don't say what no one said. We never said products have negative energy. They have less. What is negative is the delta H, energy transfer, heat transferred. It's negative because products have less. We'll see how to calculate it. Here we are seeing diagrams and things. So why is delta H negative? The system has lost energy. The system has lost energy, okay, to the surroundings. So it is negative. And now, here, this is, okay, examples is anytime you burn a fuel, you feel it. Anytime when you see a reaction producing heat, it's exothermic. It's releasing to the surroundings. So burning fuels or any type of fuel, then acid plus base reaction, then rusting and burning, whatever. These are all examples of exothermic reactions. They release heat. Uses of them. Look at these uses. When you're burning gas to cook, when you're burning wood to cook or do whatever, when you have coffee cans that are self-heating to keep your coffee warm, when you have hand warmers that you hold like it's a plastic that will be releasing heat like this, you put your hands and you feel warm, stuff like that. These are all exothermic reactions going on. Endothermic reactions are, you see, look at the glass, look at the container, students. You can see that this container is cold. The container is cold. The surroundings become cooler or colder. When you put your hands on the container, you will feel coldness. It's because heat is going into the system. Remember, the container is not the system. Don't ever let me down. The container is the surroundings. So if the container is cold, the surroundings are cold. This thing is getting heat from the surroundings. This is an endothermic reaction. Now, how do you define it? Let's define it here. It is a reaction that transfers thermal energy from surroundings to system. So remember, it's either from system to surroundings or from surroundings to system. This is how you define and get your 1 mark or 2 marks depending on the question. Now, here, we know that both things will happen. Bonds break, new bonds form, but at the end of the day, for it to be an endo, it's taking, that means the breaking was more than the one that was released when new bonds were formed. This endothermic, it will make sure it takes heat. Extra energy is taken from the surroundings. More energy is needed to break bonds than is released when new bonds form. We know that both things happen, but when we say overally, this reaction takes thermal energy from the surroundings to the system, then we know that more energy is used in breaking bonds than in forming bonds, than released when forming bonds. When you do the energy profile diagram, you do it like this. You start low, because at the end of the day, the products will have more energy than the reactants because it was taking energy. Endothermic was taking, it was not playing around. It was taking energy and giving it to the system. So the system, which is the products, will have more, the products at the end of the day, than the reactants, which were the old system. So here's your reactants. They started low. The products will end higher. Now, what are some labeling that you must know? Always label from reactants to the top of the mountain. And this, call it the activation energy. Always label from reactants to the top of the mountain. And also always label from reactants to product and call it delta H. And you have done well. This is going to be energy transferred in kilojoules. Then this is going to be time. What happens with time? Delta H is from reactants to products. Ah, is this O? Yes. Is this O? Yes. Now it leads you to, okay, here are some characteristics. We said products have more energy than reactants. And when you're going to calculate delta H, you get it as positive because heat is taken from the surroundings. So the delta H is going up. So it's going to be positive. You get a positive when you calculate it. Right? And it feels cold when you hold the container, which is the surroundings. They feel cold because heat is coming, energy transfer, the thermal energy is transferred from the surroundings to the system, which means the temperature of the surroundings will decrease. They are losing thermal energy. Their temperature will decrease. All right. Examples of endothermic reaction. This is important. A typical example of an endothermic reaction. Any reaction you need energy for it to happen. Any reaction that needs energy to happen. Electrolysis, photosynthesis. Photosynthesis needs energy to happen from the sun. The fact that it needs energy makes it endo. If it didn't need energy, it would be exo. Now, thermal decomposition means you are using heat to break down things. This is also an example. Here are some everyday examples. Photosynthesis, like we said, for food. This is important. And cold packs, and whatever processes that you have that dissolve things. When things are dissolving, they are taking energy. So this is endo. All right, so here is the exo versus endo. This endo will be a cold container. Container feels cold. Exothermic, the container is hot. It's releasing energy to the surroundings. The temperature of the surroundings increase when it's exo because it's releasing energy to the surroundings. Here they decrease because it's taking energy from the surroundings. All right. The products have lower energy for exo. They are losing. It's a loser. It's losing energy to the surroundings. So the products have lower energy than the reactants. But for endothermic, the products have higher. Don't let us down. And then delta H is going to be a key thing. Once you calculate, you get your delta H being negative. That's a loser there. It's losing energy to the surroundings. When you calculate and get delta H being positive, hooray! It's an endothermic, so the system is gaining. It loses nothing. It doesn't want to lose anything. Anyway, now here I want to go to the last part. Okay, let's talk about this activation energy because it's going to be very important. Students, I don't want to talk too much about it because we're going to talk about collision theory tomorrow. And maybe it's the time that I'm going to make you understand activation energy better. Let me jump because collision theory is going to be tomorrow. Now, last thing is, how do you, energy profile diagrams I've taught you. Here, I want you to know the last thing. Bond energy calculation. This is the last thing I want you to know, and you're done. And we can do questions on chapter 5. Okay? We'll do questions on chapter 5 easily. Bond energy calculation. Bond energy, it looks at how much energy is needed to break the bond, or how much energy is released when the bond forms. Whichever is bigger. Here, when you look at a bond energy, let me tell you, you get a table, okay? And the table will be giving you bond energies of different types of bonds. Look at this. They'll tell you the bond between a hydrogen and a hydrogen, the energy is this. This is telling you what? If they say the bond energy between a hydrogen and a hydrogen, it tells you how much energy is needed to break this bond. So when you see 436 here, it tells you you need 436 kilojoules to break this bond. And it also is telling you that you are going to release 436 kilojoules when you form this bond. So wherever it is being formed, you are going to release. And releasing leads us to negative values. So we will be subtracting any release. Releasing is a loss. That's a loser. So bond energy, this bond energy We said it tells you how much energy you need to break this bond, or how much energy you release when forming the bond. So what you will do, the most important thing, they can ask you, listen now, this is back to what we were doing in maths. Some of the things that I do not allow anyone to forget from yesterday when we did maths. I said, and this is the secret that I teach young people, okay, who are writing next year, but I can make you understand it and master it because I want you to get the best grades ever. You don't answer any question. Listen. Seth Akimasvita, I'm telling you right now, and know this forever. I will not take any question that is ever answered without a formula. I don't care whether you know it. You may be Mr. Albert Einstein of 2026. You don't need the formula to do it. But let me tell you something, my friend. I will not look at it if the formula is not there. Because this is the secret to you getting hidden things anytime. Whenever you do a question, you write the formula that works for that situation. So here, they may ask you how much energy was taken in to break the bonds, or how much energy was given out to break when breaking the bond. Or they can ask you how much energy is in the CH bond. They can ask you anything. I don't care what they ask you. I want to see this statement. I want to see this formula. Before you do any bond energy calculation, please do me a favor. Do not let me down. Don't disappoint me. Put this formula, and then you can do your bond energy calculations. Delta H, okay? It's almost like Pythagoras theorem. We don't look for missing sides before we have written Pythagoras theorem, what it says. That's what you do here for bond energy calculations. You say, look, this is where I need you to remember energy taken in, okay, when breaking bonds, if you want to put in full. Minus energy released. Energy released when forming bonds. You write in full to show Cambridge, hey man, I know the formula. Then you start putting things. Don't put one statement, one word, one number, one anything without doing this. I don't want to see it. Please. Make sure you do this bond energy. Then from there, you now take it to the next, to the next, to the next. I'm going to do a lot of questions on bond energy calculations, but that's not where it's, that's just practice. What I want you to know as the last thing is this formula. May this formula be the first thing you write for any question. I shall not look at anything else. Whether they ask you to find a missing bond or what, that's not the issue. The issue is not the missing bond. The issue is what formula is used in this section. Always start with that. Then from there, you start moving to the other things. Have you heard me? Are we together? Are we on the same page? Right. Have this as your last thing and you'll be done. So I'm going to share with you this document. Just look at the things I've shown you. Those are the important things. And if you know them, you're fine. We do chapter 6 in our next chem lesson. And I'm going to talk about the 3 sections of chapter 6. Redox, I'll talk about it. Equilibrium, I'll talk about it. Rate of reaction, where everything starts. So it starts with the rate of reaction. We do equilibrium, which is a completely different. Don't mix it up. Rate of reaction has nothing to do with equilibrium. Equilibrium has nothing to do with redox. So we're going to do those 3. Then you know you're done. And we look at questions together. We see how good we are. Are we together? I'll give you a few questions, maybe 5 or 6, just so that I have you staying active. Anyone with a question on this? Of course, I'm sending you the physics questions from past papers that I promised you. But anyone who has any other question? Anyone with a question? Okay. Thank you, everybody. It's now time for Gio. You're dismissed. Anyone else?